It's a blur.
Yeah.
Oh, sorry. And give me the right word. You said it wrong. Give me the right one. Why is it so?
Blurry.
Thank you. Did you write this down, Coulomb's law?
Is blur adjective or a noun?
It's a verb.
It's a verb.
Yeah, to blur something.
Oh.
I mean, you know, to make it blurry. Like, blurred the truth.
No.
Like something like this, you know. Okay, you got this?
No.
Okay.
Yeah?
Mm-hmm.
Got it?
Mhm.
Okay, Coulomb's law. Now, you remember that a point charge will produce an electric field. Let's examine the force of attraction or repulsion between these charges. So, you remember that, or I don't know, I hope you remember the formula. Let's say that this is a positive here, and let's say there's a positive over here as well. This will make a field. I just care about that piece. Does anybody remember the formula for the strength of a field? The E.
QEB. BN.
That's the one I'm looking for, thank you. The E here, remember, is 1 over 4 pi epsilon 0. And we call this Q1. Q1 over R squared. And this is the distance R. Do you remember this? I hope so. Do you? Now, what's the formula for F? QE. So the force here, the force here will be Q2E, because if this is a Q2. So by putting these formulas together, you can get F equals 1 over 4 pi epsilon 0 Q1 over R squared.
Q2.
That's the E times Q2. Or in other words, Q1, Q2, and remember we can call this just a K constant if we want. This is on your calculator, this constant. This one is not, but this one's actually in the formula book.
Oh.
So, whichever you prefer. If you want to use your calculator, you'll have to type it like this. If you want to just use a K, one number, you can look it up in the formula book. It's at the front. Whichever you prefer. So, this here, obviously important. Maybe you want to write it down and we'll continue with the slides.
Should we drive in the future?
If you want to.
Teacher,
Yes.
let's try before to class. It is.
Similar, we'll talk about that, yeah. You're right, Jerry. You're right. You don't usually drink Coke, do you?
No, you always drink.
Yeah. In the morning? You see, because I have you at 2 o'clock, I'm seeing things I've never seen before.
This is the one you've never seen.
Yeah, never seen this before. Never seen you drink Coke before. It's all strange. Never seen you eat chocolate biscuits before. It's all strange. Continue? No? Yeah? So, Coulomb's law states this, where F is the force between them, Q1, Q2 are charges, and R is the distance between them, and K is a constant, and the value is actually 8.99 times 10 to the 9, and the units are Newton meter squared per Coulomb squared. You might want to write the K value down, that might be helpful to you.
Are you going to give the K value or the K equal to 1 over 4 pi epsilon?
In the formula book, I believe they use a K.
I mean, K is equal to 8.9.
That's in the formula book. Yeah. Okay. Yeah?
1 over 4 pi epsilon 0 is...
K.
Yes.
Yeah, same value. The epsilon 0 is on the calculator. The K is not though.
I mean, how can it be like 10 to the 9 power?
I think it's because the epsilon 0 is so small. It's a small number. The other thing, KJ, is if you study this next year in more details, you'll discuss epsilon 0 in more details. Okay, continue. Yeah? So, let's examine how Coulomb's law applies here. So, if the force is the same, if the forces are the same, why does the electron move and not the proton? Like if Coulomb's law says the force here is Q1, Q2, you know, blah, 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 but also the force here is Q1, Q2 over blah, 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 which means the forces are equal here. The force the proton pulls on the electron is actually equal to the force the electron is pulling the proton with. So if it's the same force, then why is it the electron moves around the proton and not the proton around the electron? It's because the mass, and we actually talked about this, I think, in an earlier worksheet, I don't remember which. Because the proton is heavier, it pulls the electron around, because it's not really the force that matters, but the acceleration. And the acceleration is force divided by mass. So here, the acceleration is force divided by a small mass, which is quite big. And here the acceleration is force divided by a big mass, which is quite small. So there is not much acceleration here, but there is quite a lot here, which I just explained. But I think we often just ignore the proton and just look at the electron's movement. Although technically speaking, the proton is vibrating, sort of simple harmonic motion. Right, when one charge Q, small q, is trapped in a circular orbit around another charge, big Q, then it will have negative potential energy. Why am I saying negative? Well, because it's trapped. And we talked about this before. What is the formula for the potential energy? It's actually kind of similar to the formula for the force with Coulomb, except there's really two differences only. What's the difference here?
R.
The R instead of R squared, and also, well, the Q's, this is still Q1, Q2, it's the same thing. Yeah, the minus is to remind me that because it's trapped, this should be a minus. Yeah? So this is the formula for potential energy. Now this actually turns out to be quite useful to something you do in chemistry. So in my picture here, I'm picturing something like this. This is a big charge, we'll call it plus Q. And this is a small charge, and I'll say it's a minus Q because I want it trapped. The potential energy here is minus K Q over 4. Now to be really, really strict about it, if it's trapped, this has to be a minus, so I might want to write this to make it very clear. I'm saying it's a negative number because it's trapped. This one's trapped. Oh, what is the word trapped? Oh, can someone tell him so I don't get angry?
Oh, so do we have to write down the minus in final or
Oh yeah, you should have a negative answer.
or this one should.
I'm putting the minus there to remind us it's a negative answer.
Yeah, it looks like
Yeah.
you know,
How it can be plus?
It could be positive if they're the same charge, and are being pushed away. I should really have said in this definition for opposite charges, because that's the only way you can have something trapped. Because if there's two positive charges, you can't trap them. They'll always want to separate. So that's how it could be positive potential energy. Actually, maybe I'll make a note. I'll try to remember to add that in. It's worth saying. Okay, continue. Yeah. Yes. Continue. Oops. Okay. Coulomb's law gives the size of the force between two charges. This force, the force between the charges, is one of actually four fundamental forces in nature. There's actually four natural forces. Now we have one of them. The force between charged particles. The force that pushes protons away or pulls protons and electrons together. That is one of the four forces, this Coulomb force. What do you think the other three might be? Gravity is the other one. Oh, and I should say, when I say Coulomb's force, I mean all the field forces are actually counted as this. The magnets, the electric field, Coulombs, they're all because of a charge. So this is all the one force. Gravity is the other force. There's two more forces. I wonder if anyone knows them. No, but this isn't like something that causes a force in nature, not a type of force. Like friction is a type of force, but I mean a force that occurs in nature, a naturally occurring force. Opposite direction.
Atmosphere strength.
Say again, yeah?
Atmosphere.
Atmosphere, no.
What is a natural force?
Oh, okay.
There's four natural forces in life, in the universe. Gravity is one, Coulombs is another, and there's two more. What?
Earth.
No. You don't know, that's fine. Huh? Not pressure, no. There's two more forces we will study in the chapter on atoms, and these are the forces responsible for keeping the atom held together. The nuclear forces. Yes, we'll do that in a later chapter. Huh? There's two types of nuclear forces. Yeah. Okay. Interestingly, Coulomb's law is an example of an inverse square law in physics. These are surprisingly common, and it's worth looking at what the reason might be. So by inverse square law, what I mean is it's a law that has a square in the bottom. F equals K Q1 Q2 over R squared. There's actually a lot of formulas in physics that has a 1 over R squared in it. Another formula which we haven't done yet, but maybe you remember it if you've done it at school, is this one. As Jerry, you said you remembered this one. Yeah. Do you notice both these formulas have an R squared in it? In fact, a lot of physics formulas have an R squared in the denominator. Yeah? A equals what? Oh, the acceleration for the yeah, no, not this one. Not this one. That's V squared over R. Isn't it? Yeah. I think so. Yeah. Anyways, let me explain the reason why these laws are so common in physics. We'll make up an example, okay? Here is a student, and they stink. Smelly student. And here I have a little machine which detects the smell. We'll measure the unit. What unit could we use for smell? Yeah. Stinks per minute or something. Smell per minute or something. It measures stinks per minute. Smells per minute. Now, we want to know what is the value of the force of the smell here. So we try to guess the formula. So we can say the smell is, well, it's going to be some constant, right? What in the formula at the front. And it's going to depend on maybe how smelly the student is. So maybe we'll call that, I don't know, what letter do we use? S1. S1. smell. But think about what's happening here. The smell comes out, but it gets spread over a bigger and bigger area each second. So for example, if there's 1 smell per minute coming out, then here there's also 1, but it's spread over a bigger area. And here again, it's still 1 smell, but it's spread over a bigger area. So by the time it gets to here, it's spread over a very big area. So what happens is this smell, this 1 smell per minute, you're dividing it by the area. It's being shared over the area. Now what shape is this? It's a sphere. It's a sphere that expands out. And the area for a sphere is 4 pi r squared. So that means down below we should have a 4 pi r squared. Now all of a sudden this maybe makes sense of why there's the 4 pi in the Coulombs formula. But we could just put the 4 pi inside the constant and we're just left with a constant, another constant over the distance squared. Now you don't need to write this down. This isn't on the course. But I felt it really important to tell you and give you a reason why you will see so many formulas that are an r squared in them. It's a good reason. When things tend to spread out, it's usually by this formula. Now sometimes it's actually an r cubed or an r4. And when that happens, it's because the thing that's spreading out is disappearing quickly. It's decaying. Maybe it's getting soaked up by the air or something like that. Yeah? Anyways, you don't need to write this down. I just thought it's important that you see a reason why you will see so many formulas here. Yeah?
What gravitational force?
It's the same idea actually. It's like the gravity is getting spread out over a bigger area as it expands out from the object.
Doesn't have shape or something.
What exactly? The gravity? It's just kind of like a... We'll actually look at the gravity fields later in the chapter, so it is something we'll study, but unlike the electric and magnetic fields, it's not really that interesting. It's just kind of a straight sphere, just spreading out. Now, before continuing, I want you to notice something. The K is actually a very large value. It was 8.99 multiplied 10 to the... No. Plus 9. Did you write minus 9? Yeah. Now, that will be important later and worth talking about again later. Right, here's a small one for you to try. What is the force of attraction between a proton and an electron, which are 0.1 nanometers apart? I'd like you to use Coulomb's formula and tell me the force here, please. K Q1 Q2 over r squared. Calculate, please. Coulomb's formula. We got answers? Let's have a look. 8.99 times 10 to the power of 9. E times E over 0.1 times 10 to the power of minus 9. So, the force between the proton and the electron is still pretty small. It's measured in nanos. 23.1 nanometers.
Will you
Yeah.
have to put negative on the other direction?
The minus is only going to tell us the direction, and I already asked the question what is the attraction force, so you don't need to give the direction again. Continue? Continue, guys? Right. Here's another one for you to try. A little bit harder now. How long does it take an electron to orbit a proton? And the distance is 0.2 nanometers. So, what's the time for the electron to orbit the proton? That's the next question now.
How long? K equal omega r. Is that the formula? Omega.
No, omega squared or.
Oh. And what is omega? 1 over 2 pi t over.
Omega is 2 pi over t.
I forgot the formula.
Have you got an egg?
I know, I'm not gonna know. times 10 to the power negative 16.
16?
Second.
That sounds too small.
Too small?
I was expecting like nanoseconds.
Gosh.
Let's have a look.
We
Oh, right. Okay. What?
Yeah, wait. Oh, because I used the previous force, then I realized they have a different radius.
What you say?
I used the previous
No, the word at the end.
I thought that should be the same one, that's trying to run for.
Get an answer?
What
Did you get an answer?
Yes, so
What you get?
I won't tell you.
Okay, fine. What did you get?
0.012.
That sounds too big.
The minus is
Monica, did you get an answer?
10 minus 15.
Alright, let me do it. Let me do it. So, proton, electron, 0.2 nanometers. So, F equals ma equals mv squared over r. But b equals omega r. So this is m omega squared r squared over r, which is m omega squared r. But some of you knew that already. But omega equals 2 pi over t. So this is m 2 pi over t squared r, which is 4 pi squared m r over t squared. Yeah? But this here is equal to k q1 q2 over r squared is equal to 4 pi squared m r over t squared. Now, we can rearrange this. We can get t equals square root 4 pi squared m, and to be clear, which m is this? This is for the electron, or cubed over k, and the charge is e and another e, which is e squared. So we can simplify this down a little bit. T equals 2 pi over e square root mass of electron or cubed over k. This is as simple as I can make it before I have to put numbers in, which I will do right now. No? Oh yes, well, but then I have to type or twice, one on the inside and one on the outside. I'm making it as easy for me to type. You know.
I thought that's a lot.
No, it's not. What are you talking about? 2 pi over e square root mass of an electron, which is number 3, isn't it? Over 8.99 times 10 to the power of 9. And this is a thingy cubed, 0.2 times 10 to the power of minus 9. Now maybe your answer's right. We'll find out right now. It is. Good job. That's very cute. 1.12 times 10 to the minus 15 seconds. Let me think now. 6 is micro, 9 is nano, 12 is pico, so 15 is femto? Is this 1.12 femtoseconds?
That's not good.
Ah, come on, you love this, I know you do.
Oh,
No, I love 10 to the minus.
just add.
I think it's 10 to the minus 15
Yeah.
femtoseconds. I think. Does anyone know for certain?
I love 10 to 15.
Yeah, no, that's fine.
Yeah.
But this is better.
Maybe she should.
You okay?
Yes.
Are you sure?
Yeah, I'm using 2 pi, then square root m over e cubed, then
E cubed?
yeah.
How'd you get E cubed?
No, e cubed, e cubed.
Ah. What's the cube?
Cube is the charge of the electron.
Which is also E.
The e is the k cube over r squared.
Which is the
Big
same.
E or small e?
Big E.
Ah, right, that's fine.
What?
Yeah, that's the formula.
Yeah.
Also, you also use that for
Yeah,
No, it's the same.
You see the big
yeah.
is what?
F over Q.
The big E is Q1, Q2 over R2.
Correct. No. Oh wait, sorry. Oh, you said QQ.
Oh my god.
Continue.
You know what the chapter minus thing was?
I do.
What is that?
Just give me the first letter. The first letter.
First letter is everything.
Is it?
Yeah.
What is that?
Yes.
Ah, Zapto.
Wow. Why do you remember it?
Close enough. Yeah.
Zapto.
No, it's not Zeta. Because Zeta is a Greek letter. I know it's not that. Zapto. Yeah.
Zapto.
Oh, and there's an exo as well, isn't there? Huh? Exo.
I guess no.
Don't know.
You're right. Do you need to write this down? You do, because you wrote it down. Lee!
No, we don't have accent.
Just previously you did very easily, like XR over EQ.
Yep, life gets harder. Life gets harder and tougher, and there's more problems. You'll discover this. Then
But
you
it
get
will be
it.
better if you have a kid.
You really think so? I won't correct you. I'll let you believe that. I don't want to shatter your worldview.
Gosh, I'm good with my parents, so yeah.
Now, that's what you think. If I had an honest conversation with them, you know, they might say something else. You don't know.
I'm down to.
They might say, "Well, Lee, he's all right, but no, you don't need to say. I understand, Mr. and Mr. Wynn." Okay, continue. Yep, you have this written down, Sean. Yep. Did you get the right answer?
No.
What did you do wrong?
I forgot the formula.
That is a problem. Right. This is a shorter one. How much potential energy does an orbiting electron have if it's orbiting a proton at this distance? Okay, this one is much easier. I hope you get this one right. Be careful. Don't forget, there's no square in this formula. Did I? It's a bit like, actually, no, it is that problem in English when people, it does happen a lot. For example, when people, describe to me where you go to get cash out in the wall. What would you say? Yeah, well, give me a full sentence, like, describe what you're going to do. I'm going. Yeah? You won't stick any word after ATM? Because some people would say the ATM machine. The machine's already. Yes, I know. Of course, I know this. You have an answer, KJ? Uh-huh. I realise, KJ, you're getting very advanced now. You have your graphing calculator, you have your electric skateboard. I wonder. I wonder what we'll see next. Will he just come in with like an Oculus Rift on or something, saying, "I'm ready for physics. Let's go." I can see the equations. Okay, we have an answer? Who's your maths teacher? I forget. Oh, it's me, isn't it? No, I was thinking actually the January students, I teach them physics, but I don't teach them maths. Ivan. Ivan. Not Ivan, no. Huh? What?
She looks scary.
You think so?
Yeah. She looks like
That's zero.
I heard that one of the math teachers gave them a lot of work to do, a lot of
But
homework.
was their name sound like Stephen?
No.
Because I don't.
I mean, I heard from other students.
Minus 18.
Might be Joan. Joan likes to give a lot of questions. I used to give the most questions. I relaxed a bit. Aren't you lucky? Okay, we have an answer here?
Yes, probably.
What you get?
1.538
With a minus?
to the minus 18.
Okay, let's see. So it's minus
Over
K times, it's just E and E, isn't it? So I'll just write E squared. And the distance? Now, because this unit, this energy level is so small, rather than using joules, what would be a more appropriate unit, perhaps?
Picojoule.
Hey, Joel.
F-joule.
No. Remember, we have a special unit,
E-joule. Yeah, electron joule.
electron volts. Electron volts. How do I convert this into electron volts?
It's not even volts. It is joule.
But it doesn't matter. Electron volt is just a small energy unit. So how do I convert this into electron volt?
Divided by electron.
Yeah. So I wonder if that will make it less small. It will make it less small. Yeah, that's much nicer. You can say the energy is minus 9.6 electron volts.
But do we need a minus?
Yes, we do, because it's trapped. That's what you should have. Now please be careful in the exam. Sometimes they want the answer in electron volts, and usually they'll tell you that. But here's my tip, so to speak. The moment you get smaller than 10 to the minus 9, you want to start thinking about using electron volts. Because at 10 to the minus 9 you can still say nanojoules. But once you get smaller than this, if you felt brave enough you could. But here you see, what did I have previously? What power? Minus 18.
Zito.
Yeah.
Zito.
But it's likely that you'll screw it up in the exam, believe it or not. Yeah? So just keep it in this form. But if they insist on having a simpler unit, it's going to be electron volts because it's so small. And this is actually quite a nice way to give the answer. Minus 9.6 electron volts. It means it's the same amount of energy a group of about 10 electrons would have if they entered a field which was under a potential difference of 1 volt. Okay. A couple of questions here. You can take a picture if you want, and then we'll finish there.
No, don't find my finger.
Please stop picking on Jerry. Stop bullying Jerry.
Hi.
Yeah. Yeah, you. Yeah.
You.
Yeah. I only saw you bullying Jerry now. Jerry's a good boy. Leave him alone. Yeah, exactly. Yeah. That's true. He's only a minor now, you know. You should be taking care of him. You know, make sure he gets the class all right.
No, he is no minor.
He takes the right bus home, you know.
I'm on this at all. Don't trust me.
You're what? That's true, yes, he has rights, okay?
No, it is now.
Don't touch me.
Exactly, yes, true.
Don't touch me.
Don't touch him.
Don't say wrong words of it.
And then you're going to touch me.
He doesn't know, he's only a boy, he doesn't know what he's doing.
Yeah.
Yeah.
Oh, you should just let
Yeah.
me touch me,
Yeah.
so I touch you.
Weird. Alright, can I close this now? Sean, what's taking so long?
Focus.
Instagram filter. It's going to have a nose and 2 ears on the top. Dog filter, yes, yeah. Alright, I can close it now, yeah?